All right, so now we move on to lesson 5.3, part 2, and that's dealing with more radical equations, but in a more complicated form. Now, when we look at these more complicated forms, a lot of the problem solving will be very similar. So to start, we're always going to state the domain or restrictions, just like we did in our previous lesson of part 1. We're then going to want to isolate one of the radicals, which in this situation, that's one of the new steps here, is isolate one of the radicals. It's because when we have this, we have that there is going to be two radicals in most of these problems today. So we need to figure out how do we make sure that the radicals are isolated on each side such that we can square them and then get rid of the radicals from both. And then if the radical still remains after that first square rooting, we might have to square it again on both sides. And so that is another new thing we're going to add today is not only we're going to state our domain just like we've done before, we're going to undo the radical by squaring, which we've done before. We might have to repeat the process more than once. All the other steps are very similar because we're just going to solve for the variable and then verify our solution. Now, in this situation, these are a little bit applied for sure, for the most part. So let's see if we go to the first one here. Again, we're going to want to look at these and be like, okay, now we see a double radical, which means we have to consider some sort of situation where we're going to have to account for there being two restrictions. So the first restriction is where x minus 1 is greater than or equal to 0. The other restriction is going to be where 2x plus 3 is greater than or equal to 0. Now, in both of these cases here, and the reason I'm using a little bit smaller of a pen here is that we got to create some space for the problem. And maybe what I'll even do is just bring them closer together just to maximize as much space as possible here. There we go. We're going to isolate these and we're going to go, well, if I add 1 to both sides, it's x is greater than or equal to 1. We then have on the other one, this is going to be x is greater than or equal to negative 3 over 2 if we isolate it for the x. And now we want to account for both of these. And so one of these restrictions goes for both of them, and the other one, unfortunately, is just already included in it. So we're going to look at this and let's consider a number line here. So I'm going to draw a number line just right below this. And on this number line, I'm going to put the x values. First one, x value is going to be negative 3 over 2. I'm then going to put an x value of 1 over here. And now what we're going to do is we're just going to use the number line to indicate where the solutions exist. For 3 over 2, we know that it's going to be greater than or equal to, so I'm going to draw an arrow off to the right. For the 1, we also know it's greater than or equal to. And if this is the case, we can actually even put a solid dot on both these locations because it's actually included. Where does it account for both of them? It's where it's greater than 1. We need to look for those regions where both of the arrows are overlapped, because if both of the arrows overlap at this point here, and I'll backpedal that just so that we can include the 1 here, if the arrows both are included here, it means that this domain satisfies both of the radicals. We wouldn't want to pick a value less than 1, or else the one side wouldn't be able to equal a real number, and we would get something that's not appropriate for this. So when we look at our restriction, I want you to highlight x is greater than or equal to 1, because this accounts for both radicals having real numbers. Okay, now that we've done our restriction here, let's go down and solve. So we're going to go to step number 2. Again, just like in our previous lesson, I'm going to take these radicals and rewrite them. So it's going to be x minus 1 on the left. On the right-hand side, it's going to be the square root of 2x plus 3. Just making sure it's positive, which yes, it is. There we go. Now what we're going to do is we're going to square both sides in order to get rid of the square roots on both. This is going to give us x minus 1 is equal to 2x plus 3. Once we have this format, what we want to do is then isolate for x. So I'm going to maybe subtract away x from both sides. This will end up giving me negative 1 is equal to x plus 3. I'm then going to subtract the 3 across from both sides, which I realistically could have done on that previous step. And this will give me x is equal to negative 4. Now, if we get x equals negative 4, again, before we can actually confirm this is a solution, we need to make sure we plug it in for the brackets and check it with the inequalities. So let's say we go down to, or let's say we go up to our inequality where we had to state our given restriction. Our restriction was that x had to be greater than or equal to 1. So if it has to be greater than or equal to 1, is negative 4 greater than or equal to 1? No. So what we can do right away is as soon as you see this situation, I want you to circle this solution, put a line through it, and be like, this must be extraneous. Now, on top of this, just to make sure that this is actually true, we would always want to plug it into the two radicals and verify that this is true. So for step number 3, I'm just going to plug it in and be like, well, we know the square root of, our first square root was x minus 1, which was negative 4 minus 1, which is equal to the square root of, on my other radical, 2x plus 3, aka 2 times negative 4, and then plus 3. Now, if this is the case, we need to realize that this left-hand side will be equal to negative 5 square rooted, which is equal to the square root of 2 times negative 4 is negative 8, negative 8 plus 3 is negative 5, and you'd be like, okay, well, I mean, they're equal to each other, so square root of negative 5, square root of negative 5. However, in this unit, we cannot have a square root of a negative number because this creates an imaginary number. So this cannot happen, and that's what I'm going to summarize. Cannot happen. And I'm going to say you cannot square root a negative number like this. And I'll just put this here and then put a circle with a line through it, just indicating that it's like we can't square root negative numbers. As soon as we square root negative numbers, we're like, this clearly shouldn't happen. And therefore, as soon as you get that square root of a negative, even if the two sides are equal to each other, this represents an imaginary solution. And we don't like this. And we don't even talk about imaginary numbers until the university level. So we really don't want to be focusing much on this. You will have tools to establish these once you get to the university level. If you take any sort of STEM program, you might talk about this. But at our level, we never go into that. We only talk about the real numbers. Okay, let's shuffle over to part B. So part B is going to get us to consider the following two here. And so actually, and I should even go back to this one here just very quickly. We can also summarize this instead of just saying extraneous. You could say that there's no solutions that satisfy this. So maybe that's something we should include just off to the side here. Is we could be like, therefore, there is no real solution. Perfect, because there's some are imaginary solution, but we don't want to talk about imaginaries just like we said before. Okay, now we can go over to part B. So if we see this type of problem, what I'm going to do right away is I want to establish what are the restrictions. So for part number 1, x minus 7 must be greater than or equal to 0 because it's the one radical. The other one, 2x plus 4, which is the radicand of the second radical, is greater than 0. This means x must be greater than or equal to 7, and that x must be greater than or equal to negative 4 over 2, which also just simplifies to greater than or equal to, and maybe I should just put equals to negative 2. Now, let's draw a number line just to see what this looks like. So I draw a number line below. I put the two numbers on the number line. So let's say I put a hash here and a hash here. This is going to be the negative 2, which is the lesser of the values, 7 over here. Let's represent using arrows. It's greater than 2, so we're going to put an arrow going to the right. We also have greater than 7, so an arrow going to the right. And we can even put a dot here and make sure I use the right tool there, dot here, and a dot here representing that they are included. And then just like our last problem, you want to circle the area in which they both overlap. They both overlap as long as it's greater than 7, both radicals, not inequalities, but both radicals are satisfied as real numbers. So our restriction is therefore that x must be greater than 7. This accounts for both of them. Now for part 2, let's see if we can actually figure out what this x value is that satisfies for both of these situations. To do that, again, I always like to write the original. So if this is the square root of x minus 7, which is equal to the square root of 2x plus 4 over 2. What I'm going to do is I'm going to start by multiplying both sides by 2. I think that's a pretty logical step here. And maybe I'll use red just for consistency here of showing algebraic steps. I'm going to multiply by 2 because I don't really like that 2 in the denominator. Not that it matters much, but I think it's sometimes maybe important to get rid of it. This is going to make it 2 radical x minus 7, which is equal to the radical of 2x plus 4. Now from here I can square both sides, so I'm going to go square and square. Now when I square both sides, 2 squared is equal to 4. The x minus 7, which was included under the radical, just is now x minus 7, which is equal to, on the right-hand side, 2x plus 4. And what I want you realizing once you get to this step here is make sure that you've put brackets around this term here. Reason is because if you forget the brackets, you might just write it as 4x minus 7, and we don't want that. We know that the 4 will get expanded to both of these. Now, in expanding this, this becomes 4x minus 28 is equal to 2x plus 4. Now what I'm going to do is isolate for x, and I'm going to do kind of 2 steps in one. I'm going to subtract the 2x's from both sides, but at the same time, I'm also going to add 28 if I know that I'm moving my x's over to the left. Now this is going to give us 2x is equal to 4 plus 28 is 32. We divide both sides by the 2 to isolate the x, and we end up getting that x is equal to 16. Now, we're not 100% sure if this is the solution, so now we need to go to step number 3, which is to verify this. To do step number 3, let's just take a look at where our problem is and how much space we have. Yeah, maybe we go off on the right-hand side here. So I'm going to go step number 3. Let's just verify and see if this works. We are going to go right back to the original. So the very original statement was the square root of x, which in this case is 16 minus 7, is equal to the square root of 2 times the x value, which was 16, plus the 4, which was here, all divided by the 2. Now, 16 minus 7, this is going to end up giving us the square root of 9. So square root of 9 is equal to, in the other one, it's 32 plus 4. 32 plus 4 is 36. Square root of 36 in the numerator divided by 2. That means, therefore, we get 9 square rooted, which is 3, is equal to the square root of 3, which is 36, divided by 2. Or, sorry, square root of 36 is 6. 6 divided by 2 is equal to 3. Therefore, the left-hand side is equal to the right-hand side. And as soon as you can prove LS equals RS, you know that this solution is a satisfiable solution. So therefore, we're like, hey, x equals 16. This seems appropriate to us, and we are happy with this. Now, I'm just going to make sure that that highlighter is just a little bit straighter. There we go. There's our problem. So again, we're following the same 3 steps we did in our previous lesson, but now we have to account for 2 different restrictions and then decide which restriction accounts for both. And then we have this double radical, but for the first couple here, it's solved pretty nicely. Now, let's go down to part C. Now, part C is going to introduce where, again, we have 2 radicals, so we always want to start with establishing the restriction. So x minus 8 is greater than 0, and then 3x minus 1 must be greater than or equal to 0. For the first restriction, it's greater than or equal to 8. For my second restriction, x must be greater than or equal to 1 over 3. And I'm kind of skipping a step in there, but I hope you understand that. Now, let's draw a number line. For my more visual people, we would start by writing out 1 mark here, 1 mark here. We put our lesser of the 2 values here. We put our greater of the 2 values here. Both of them are greater than these values, meaning they both arrow over to the right-hand side. So I arrow and arrow. And then I'm going to put dots here. And I'm going to put a dot here. And then you got to realize, where are they both the same? They're both the same, or they both overlap in this region here where it's greater than 8, meaning the restriction we want to account for is when it's greater than the 8. As long as it's greater than 8, we're happy with this, and it will satisfy both radicals. If I choose something less, let's say I chose 1, and I plug that into both, you would find that you get a non-real solution, and that's not what we want. Now, from here, let's see if we can solve it. So part number 2 here, we're going to then take these radicals and try and algebraically isolate for x. So we get x minus 8 is equal to 3. And then for this one, it's going to be 3x minus 1. There we go. We're going to square both sides as a way to get rid of the radicals. When we square both sides, it's going to end up giving us that we have 4, because 2 squared is 4. X minus 8 just becomes x minus 8 because the square and the square root undo each other, or they're opposite operations. 3 squared is 9 times the 3x minus 1. Again, we have opposite operation on the square and square root. Now from here, I'm going to distribute. So this becomes 4x minus 4 times 8. We end up getting 32, which is equal to 9 times 3, which is 27x, and then minus 9. Now, to keep the x's positive, maybe what I'm going to do is move the 4x's over to this side. And then just like we did last time, maybe I combine a step and I add 9 here, and I add 9 here. Now, this is going to end up giving us, on the left-hand side, negative 32 plus 9. This is equal to negative 23. There we go. Is equal to, on the other side, 27 minus 4. This is 23x. Now, to isolate for our x, let's just divide both sides by 23. When we divide both sides by 23, I end up getting that x is equal to negative 1. Now, we don't know if this is actually the solution, and actually what we should do right away is just double check it against our restriction. X had to be greater than or equal to positive 8. Is this greater than or equal to positive 8? Absolutely not. And if it's not, I want you to circle it, line through it, immediately write EXT, meaning extraneous, and then just to double check that this solution actually doesn't satisfy it, because our inequality is telling us it isn't. What we want to do is we want to plug this into the original radical and then see. So just like we did before, I just want to make sure I have enough room off to the right. It looks like I do. So step number 3, we're going to plug it into those inequalities. It was 2 square root of the x, which is negative 1 minus 8, is equal to 3 times the square root of 3 times negative 1 minus 1. This ends up giving us that 2 square root of negative 9 is equal to 3 square root of 3 times negative 1 is negative 3 minus 1 is negative 4. In this, what you're going to eventually find is that, again, we can't square root these negative numbers. We're like, this cannot happen. So I'm going to write that line again. So cannot happen. In the brackets, I'm even going to write that same thing, cannot square root a negative number, just like this. And then so if we see the situation, we're like, not good, I'll just provide a little bit of the context of what this actually ends up becoming. Right below this, if you actually wanted to solve this and you were getting imaginary solutions, it would look like the following. 2 times the square root of a negative number actually makes it I. Square root of 9 is 3, so this would become multiplied by 3i is equal to 3 times 2i. And then this is 6i is equal to 6i. And you'd be like, okay, well, 6i equals 6i. These are imaginary solutions. Yes, they're equal to each other on both sides, but you do not talk about this until university. So not until uni or university. I'll just put the full thing in here. And I'll put complex numbers. Now, for some of you, you may never touch these, so it's really hard to talk about these and really legitimize them because all we want you to do is just be thinking long term. Hey, for now, in our high school scope, we want to look at this and say all the way up through calculus, even for the most part, we don't want to really consider imaginary numbers at this point. Okay, and let me make sure I ignore that. Perfect. Okay, let's do our example D here. So in example D, we're going to go off, and again, we start with our two restrictions. So part number 1, I'm going to write 2x plus 5 must be greater than or equal to 0. We write 2x must be greater than or equal to 0. For our first restriction, we're going to get x is greater than or equal to negative 5 over 2. For the second restriction, we get x is greater than or equal to 0. Which one accounts for both of these? Even without a number line, what we would find is that the one that accounts for both of these is where x is greater than 0, because that's when they begin to overlap. Now, if that's the case, let's begin to solve. So for step number 2, I'm going to take the original radical of 2x plus 5, and then is equal to 2 times the 2x in the radicand plus 1. Now what I'm going to do is I need to square both sides. So I'm going to start by squaring both sides, and then this is one of those situations where you're going to notice things get a little more complicated for us. On the right hand or the left hand side, I should start, we have 2x plus 5, so we're like, that's nice. But on the other side, we actually need to expand this to be 2x plus 1 times 2 square root of 2x plus 1. We have to repeat the process more than once in this situation because the radical doesn't just simply go away and we don't just distribute it to each individual term. A binomial squared must be written twice. So now we're going to take 2x plus 5, and I'm going to write out what these become. 2 times 2 is 4. Root 2x times root 2x is times 2x because we get rid of the radical. 2 times 1 is plus 2, square root of 2x. 1 times 2 is plus 2, square root of 2x. And then lastly, 1 times 1 is just 1. Now let's collect some like terms here. We have 2x plus 5 is equal to 8x plus 4 square root of 2x plus 1 because we put together our like terms. I'm going to take these two terms, 8x and 1, and I'm going to bring them over to the other side. So minus 8x and then minus 1. This is going to end up giving us that we have negative 6x, then plus 4 is equal to 4 square root of 2x. If I can reduce these all by 4 or some number, I should. So maybe what I'm going to do is I'm just going to divide these all by 2 as a way to eliminate a factor out of here. This is going to make this negative 3x plus 2 is equal to 2 square root of 2x. Now what I'm going to do is I'm going to square both sides. So I square the right-hand side, I square the left-hand side. Again, if you have a binomial squared, you need to rewrite it twice. Negative 3x plus 2, negative 3x plus 2 is equal to 4 times the radicand, just as alone, is going to be 2x because we can get rid of our radical. Now when I expand this, it's going to give me positive 9x squared minus 6x minus 6x plus 4 is equal to 8x. Now I want to make sure that I bring it all over to one side to make it a quadratic. This is going to make it 9x squared minus 12x, and then plus 4 is equal to 8x. Let's bring our 8x's across, so I'm going to subtract them. Minus 8x minus 8x. This is going to give us something where it's 9x squared minus 20x, and then plus 4 is equal to 0. Now, this is where I'm going to recommend we plug it into quadratic formula together, because again, you're like, what ugly numbers. Like, we're getting numbers that are like, it would have to be 9 times 4, which ends up giving us the 36. What multiplies to make 36 adds to make negative 20. If you're stuck with the numbers, just be like A equals 9, B equals negative 20, and then C equals 4. What we can do is plug this into quad formula, which hopefully I have enough space over off onto the right-hand side. We might not. This one might require extra page. Let's see. Yeah, we're going to continue this one on the next page here. So I'm going to open up a new page, and I'll just make sure it is blank. Let's use this one here. Okay, in our quadratic formula, we're going to go for part D that we were just working on here. X is equal to negative b, in this case, which was negative 20, and then plus or minus the square root of negative 20 squared, and then minus 4 times a, which was 9, c, which was, let's just double check the value. I want to make sure I get it right here. C, which was 4. So we're going to plug in 4 for here. And then I want to close the bracket. I'm just going to double check signs here, making sure that's a positive 4. Yes, positive 4. B was the only negative value. And then our A value, which was 9, we're going to go 2 times 9 in the bracket here. Now, let's open up a calculator and actually plug this in if possible here. So I'm going to try and keep that all in view. Let's do our alpha y equals mode, enter. We're going to type in positive 20, because negative and negative, plus the square root of 20 squared. And again, because it's a squared, it will get rid of the negative, minus 4 times 9 times the 4 that was on the back for C, divided by 2 times 9, which is 18. That gives us x equals 2 for our first value. And then for our second value, x is going to be equal to, for our negative case, we're just going to take the exact same thing from our calculator, go up, go over to the positive, just clear that out with delete, put a negative instead, and then we end up getting that it's 222, which we should know, or that we can take this value and plug it into our calculator and go math fraction 2 over 9 is the value here. So we get 2 over 9. Now, let's just double check with our restrictions that both of these work right away before we do our verification step. So let's say I go back here and I'm looking at my question. Well, they both had to be greater than 0. And in this situation, they actually both are greater than 0. So now we need to rely on the verification to prove this. To verify it, we're going to take this original radical and plug them in for both. So I'm just going to make sure I copy down the right radical, 2x plus 5. So for step number 3, we're going to write square root of 2x plus 5, which is equal to, and then I think it was our 2 square root of 2x. And then I just want to make sure I get this last piece of it right, plus 1. Awesome. Now what we can do is we can individually plug them in here. So starting off with the first verification, I'm going to go 2 times 2 plus 5 is equal to 2 times the square root of 2 times 2 plus 1. This ends up giving us 2 times 2 is 4, plus 5 is 9. Square root of 9 is equal to 2 times the square root of 4 plus 1. This gives us 3 is equal to 2 times the square root of 4 is 2 times 2. 2 times 2 is 4, plus 1 is 5. These are not equal to each other. So therefore, we can go up to our x equals 2, circle it with our blue pen here, and then write extraneous next to it, just indicating that, hey, you know what? This is not one of the solutions. It does not work. Now what we want to do is just make sure, does 2 over 9 work? Let's double check here. So I'm going to take this and be like, if I take the square root of 2 times 2 over 9, and then I add 5, this supposedly should be equal to, on the other side, 2 times the square root of 2 times 2 over 9, all plus 1. Well, in our calculators, or even just we could do this mentally for that matter, or just even do one more step. If I take the square root of this, 2 times 2 is 4 over 9 plus 5. which is equal to 2 times the square root of 4 over 9 plus 1. In my calculator, I'll do the left-hand side piece, so I'll just leave this as 4 over 9 plus 5. And then this is going to be equal to, on my other side, square root of 4 is 2, 2 times 2 is 4, 4 over the 3, which is the square root of 9, plus 1. Now what we can do is we can just type these in and see what we get. So square root of, first of all, 4, and actually let's do this. Square root alpha y equals, I'm going to enter a fraction, 4 over 9. I'm going to put plus 5. This ends up giving us 2.33. We can do math fraction to get our value. So 7 over 3 is the left-hand side, which is equal to, over on my other side, I have a feeling it's going to be the same, 4 over 3, and then plus 1. Yes, we also get 7 over 3, or 2.33. So because our left-hand side is equal to our right-hand side, we can say that this is a valid solution. We can highlight x is equal to 2 over 9. Awesome. Okay. Now, no more problems on this page, just double checking that we're all set there, which we are. Awesome. I'm going to shuffle to these pages. Now, again, these are going to require a bit of work, so we may need an extra page if we get to them, but let's see. So to start these problems off, what we're going to do is obviously put number 1 and state our restrictions. 5x plus 4 must be greater than or equal to 0. Our other one is that 3x must be greater than or equal to 0. From here, I get that x is greater than or equal to negative 4 over 5. For my second one, I get x is greater than or equal to 0. Which one accounts for both of these? It's where x is greater than or equal to 0. So on my solutions, I need to have a value that's greater than or equal to 0 such that it accounts for both of these. Now, from here, what I'm going to then do is say, well, let's solve. So for step number 2, let's say I take my original radicals, and I just want to make sure that's a little neater there. There we go. So I'm going to take the 5x plus 4, and then plus 5 on the outside is equal to 7 plus the square root of 3x. Unfortunately, we can't totally isolate the radicals. What we could do, though, is we could reduce our numbers just a little bit in the following way. If I want to not square both sides and then have to square two radical terms with binomials, I can end up just subtracting 5 from both sides. If I subtract 5 from both sides, this is going to give me the square root of 5x plus 4, which is equal to 2 plus the square root of 3x. Now what I'm going to do is square both sides because I won't have two binomials. I don't want to have double binomials if I don't have to. This is going to end up giving me 5x plus 4, which is equal to the 2 plus square root of 3x times 2 plus the square root of 3x. From here, this is 5x plus 4 is equal to 4 plus 2 3x plus 2 times the 3x, and then plus just the radicand, because if it's the same radical multiplied by itself, 3x and 3x with the same square root, we can just write it as the value there. Now what I'm going to do is combine some terms together. So this is, again, just 5x plus 4 on my left-hand side, which is equal to 4 plus 4 root 3x plus 3x. Now, before I take the second square root, let's just make sure we get rid of the 3x from both sides and get rid of the 4. So I'm going to go minus 4 and then minus 3x from both sides. When I do this, it's going to cancel it from the right-hand side, and I get 5x minus 3x is 2x, which is equal to, because 4 and negative 4 will cancel, this gives us 4 square root of 3x over on this side. Now, what I could realistically do here is, just to simplify my life a little bit, I could divide both sides by 2. If I realize the coefficients are divisible, this gives me x is equal to the square root of 3x. And then from here, in order to figure this out, let's square both sides. So I'm going to take this side, square it, which then is going to give me x squared is equal to 3x. I'm going to take that 3x and move it over to the other side because I want to figure out this as a quadratic. Now what this is going to give me is x squared minus 3x is equal to 0. When we factor out an x, it's going to be x and x minus 3. And from quadratic equations, our two solutions are therefore x is 0 or x is equal to positive 3. Because remember, it's always opposite of what you see here. Okay, now if these are our two solutions, we need to make sure that they both work or that they're both verifiable. So what I'm going to do is I'm just going to say, well, if I figure out these two solutions, are they both greater than 0? Yes. Or greater than or equal to? Yes, they're both greater than or equal to. The other thing is we need to verify them in both situations to see if they work. So I'm going to verify them into that original equation. Maybe I just do my verification right here in the white space. So I'm going to go step number 3. We want to do our two radicals here, or we want to do our original radicals. We had 5x plus 4, or let's start off with the 0, square root of 5 times 0 plus 4, and then this was plus 5, is equal to 7 square root of 3x, or aka 3 times 0. There we go. This is going to give us the square root of 4 plus 5 is equal to 7. And I better put a plus here because I just realized there's no plus in between those. 3 times 0 like this. This is 7 plus the square root of 0, which is just 0. 4 square rooted is 2. 2 plus 5 is 7. Therefore, 7 equals 7. Our left-hand side equals our right-hand side. And we've shown that for 0, it works. So let's highlight that one. For 0, we're like, good, perfect. It satisfies not only the restriction, but also it verifies appropriately. Now let's do our second verification. We're going to take the square root of 5 times x, but instead of 0, we're going to put 3 plus 4 plus 5 on the outside is equal to 7 plus the square root of 3 times the 3, which was the x value. 5 times 3 is 15. 15 plus 4 gives us square root of 19 plus 5 is equal to 7 plus the square root of 9. This gives us, well, square root of 19 is a rational number, plus 5 is equal to 7 plus 3. That means that the square root of 19 plus 5 should be equal to 10, which square root of 19 plus 5 equals 10. This definitely is not true. So we're going to cancel all these in the middle as equals and say they are not equal to. And if they're not equal to, immediately let's go over off onto our other side here. Circle the x value, and let's just make sure that's a little neater. Circle it, line through it, write ext, and we say that as long as we know that this is extraneous and that we have one solution that works, we're like, good. Now, they both could work. We're not ruling that off the table. It's just if only one of them works, make sure that you cross out the other one and say extraneous so that I'm not thinking that you mean that they're both solutions that work. Okay, one more problem for this class, and that's dealing with this one here. So off on this side, what we're going to do is first and foremost, we see this as, okay, well, there's not much we could really realistically do in terms of algebraic isolation. Obviously, before that, we would want to make sure we do our x minus 3 is greater than 0 and our x plus 5 is greater than 0 because we want to know what x values work for this. We're going to get x is greater than or equal to positive 3 and that x is greater than or equal to negative 5. The one that accounts for both of these is where x is greater than 3. Let's just quickly show that on a number line too. If I wrote a number line below and I put two little marks, I could put my negative 5 over on the left. I could put my 3 here. If I showed using arrows what these look like, it's greater than 5, so arrow goes this way to the right. Greater than 3, arrow goes this way. Both of them have solid dots at that point because they're included. And then you're like, wait a minute, where does it account for both of these? It accounts for both of these when it's in this region here. And this region is where it's greater than or equal to 3. Okay, now that we have that out of the way, what we can do is now we can start to solve. So we have our restriction. Let's begin to solve this. It's 2, or part 2, sorry. We're going to take the square root of x minus 3 plus the square root of x plus 5, which is equal to, on our other side, which is 4. I'm going to square both sides. So take this side, square it. Take this side, square it. Now, this one's a little difficult in the following way. If we square these two on the left here, what we need to do is expand it out twice. So it's going to be x minus 3 plus the square root of x minus 5, sorry, x plus 5, I should say, bracket the square root of x minus 3 times the square root of x plus 5 is equal to 4 squared, which is 16. So the right-hand side is very easy. Now when we distribute this, and I should make sure that I don't have a double bracket in here, that might lead to some confusion. So these ones are actually a plus, not a double bracket. when I expand this out, remember, anytime we multiply the same radical by the same radical, it just becomes the term that's underneath in the radicand. So it's x minus 3 is the first term. And maybe I'll put it in brackets to organize this. Then we're going to go plus the square root of x minus 3 times the square root of x minus 5, or x plus 5. That will lead us to have the following: x minus 3 and then x plus 5 being multiplied. And I'm not going to multiply them quite yet. I'm then going to do that one more time because I see that there's another x minus 3 times an x plus 5. And then for my last term, it's going to be square root of x plus 5, square root of x plus 5, which is plus x plus 5. And this is all equal to 16. Now, let's gather some like terms here. So in the x terms, I have x and x. So that's 2x's. I'm going to write 2x. Negative 3 and 5 gives me positive 2. And then I have 2 of these square roots of x minus 3 and x plus 5. And then this is all equal to 16 on the other side. Now, let's bring across our terms here. So I'm going to take the, specifically the negative 2x and the negative 2. I'm going to bring them over here, negative 2x minus 2. When I do that, it's going to leave me with 2 square root of x minus 3 and then x plus 5, which is equal to 16 minus 2 is 14 minus the 2x that we brought across. Because these are all divisible by 2, let's just get rid of that piece. So I divide from both sides. This gives me that the square root of x minus 3 and x plus 5 is equal to 7 minus x. Now I'm going to square both sides in order to get rid of the radical. This ends up giving me that I have x minus 3 and x plus 5 is equal to 49 minus 14x plus x squared. And that's just me expanding this out and saying, well, if I know that this part here, and I'm going to maybe use a straight line tool here, if I know that this piece here, whoa, it's not giving me nice bracket here. There we go. For this one, it would become 7 minus x times 7 minus x, which would then lead us to here. Now that we have this piece here, what we're going to do is expand our left-hand side as well. It becomes x squared minus 3x plus 5x minus 15, which is equal to 49 minus 14x plus x squared. If I realize that the x squareds are 1 and 1 on both sides, I'm just going to cancel those out. So let's use a straight line tool here. I'm going to cancel this x squared, cancel this x squared. When I combine the like terms on the left, it gives me 2x, gives me 2x minus 15 is equal to 49 minus 14x. If I realize the x's can be brought over to the left-hand side and made positive, I'm going to go plus 14x plus 14x. And at the exact same time, I'm going to end up adding 15 in order to eliminate it from my left-hand side. Here's what my last step would become. 16x is equal to 49 plus 15. Well, we add 5 to the 49 gives us 54. 54 plus 10 gives us 64. We can divide both sides by the 16. And therefore, we're going to get x is equal to 4. Perfect. Okay, now we have an x value. We need to verify that this is actually true. Let's plug it back in for step number 3 and make sure that it satisfies the original radicals here. So in the verification step, and I just want to make sure these numbers are all in line here. There we go. Step number 2 is here. So step number 3, which we'll put at the very bottom here, it was the square root of 4 minus 3 plus the square root of 4 plus 5 is supposedly equal to 4. This is the square root of 1 plus the square root of 9 is equal to 4. Well, square root of 1 is 1. 1 plus square root of 9 is 3. That gives us 4 is equal to 4. And therefore, the left-hand side is equal to the right-hand side. And as soon as that we can prove that, we're going to go back to our value, highlight it, and say this is the solution here. All right. Now, these are very complex. When you see double radicals, these are not easy problems. They're very daunting on surface value. Do not feel like you're alone in feeling like these are difficult problems. There is lots more practice problems that I've just included here. So make sure that you try some of these out. See if you can do them. Realistically, these do require a bit of practice, but they are way up there in terms of difficulty. These are like on the higher end. So in terms of just assessment wise, you may see one or two of these at the very most. So be comfortable with solving them, but they're not going to be used infrequent because look at how much work they take to solve. And they are quite applied. They do take a lot of like mental taxation in order to solve these here. So yeah, these are difficult problems. Try as many as you can in terms of practice. See me tutorials if you need help, and then good luck with your overall homework.